Hello, this is a video from Erode Sengunthar Engineering College for the AICTE PRERANA scheme for preparing SC/ST students for higher education for GATE examination. So now we are going to see about the GATE preparation questions for a control system subject. Myself, Dr.M.Shyamalgowri, Associate Professor in EEE Department, Erode Sengunthar Engineering College, Tamil Nadu. So we'll see about control system. Control system is an interconnection of physical components provided to get and desired function involving same kind of controlling action in it. The control system is it is of two types. One is open loop control system, another one is closed loop control system. The open loop control system is also known as without feedback control system or non feedback control system. So for the open loop control system, the input is given to the controller. So according to the input, the controller will perform and it will produce the controlled output. So there is no control, there is no feedback in that system. So examples, automatic washing machine. In that washing machine, we are giving input, we are setting time, we are loading cloths, we are fixing time and the rinse and dry, everything we are fixing it. According to our fixation, according to the input given, the washing machine will work and the washing machine will perform the washing operation and it will produce the output. And immersion rod also an example for open loop control system. The advantages of open loop control systems are it is simple to design and it is not troubled with the problem of stability. The drawback is it is less accurate and not reliable. The optimization is not possible. What are the input we are giving to the system? According to that, the system will perform and produce the output. The transfer function of open loop control systems are Laplace transform of output divided by Laplace transform of input. C of S is a Laplace transform of output variable and R of S is a Laplace transform of input variable. Next we will see about closed loop control system. In that closed loop control system, in which the controlling action is dependent on its output. It means that the present output is taken as a feedback and it is given to the comparator. The present output is compared with the desired input. Based on the error deviation between the input and the present output, the comparator will produce an error signal, and according to the error signal, the control action is provided and the control input is getting from it, right? So the examples of a closed loop control systems are a missile launching system, a radar tracking system. In this case, each and every second, the various parameters of an missile and radar tracking system, everything is sensed, and according to the parameter variations, the control signals is provided to the system in order to correct the output and in order to achieve the desired input. The advantages are they are more accurate, reliable, faster. And the second one is the speed of the response can be greatly increased because we are control action is provided based on the error signal, so that the speed of response can be increased greatly. Disadvantages are it is more complex because we have to go for an feedback, so that they are more complex and hence cost of maintenance is high. The second drawback is it is very less stable than open loop and their oscillations in the output may occur. The transfer function of a closed loop control system is C of S by R of S is equal to G of S divided by 1 plus G of S into H of S. So here plus or minus sign is given. Here the plus sign is for negative feedback and the minus sign is for positive feedback. Here the G of S is open loop transfer function. H of S is for unity feedback gain. So we'll go to with this basic, We'll go to the questions, simple basic control system questions which may be asked in the gate examinations. First, a control system working under unknown random actions is called. The options are computer control system, digital control system, stochastic control system, adaptive control system. The answer is stochastic control system. Next, the transfer function has main applications in the study of. There are four options: steady state behavior of the system, transient behavior of the system, both of the system, none of the above. The answer is the transfer function has main application in the study of steady state behavior of the system. Next question. The transfer function of a system is defined as the Laplace transform of, first one is impulse response, second one is step response, third one is ramp response, fourth one is sinusoidal input. The answer is it is a Laplace transform of impulse response. Next question. In a feedback amplifier, the bandwidth, first option, decreases by the same amount as gain increases. Second option, increases by same amount as gain decreases. Third option, decreases by the same amount as the gain increases. Fourth option, remains unaffected. Actually, the answer is B. The answer is increases by the same amount as gain increases. Next question. As a result of introduction of feedback, which of the following is not decreases? That is, when a negative feedback is introduced in a system, one of the parameter is not decreases. The options are bandwidth, overall gain, distortion, and instability. The answer is bandwidth. When the negative feedback is introduced in a system, the bandwidth will not decrease. All other will produce variations. In a negative feedback with loop gain T, the noise generated within the basic amplifier. Options are decreases by the factor of 1 minus T, decreases by the factor of 1 plus T, increases by the factor of 1 minus T, remains unaffected by the feedback. The answer is decreases by the factor of 1 minus T. Next question. With the negative feedback in the closed loop control system, the system sensitivity to the parameter variations, whether it is increasing, decreasing, becomes zero, becomes infinite. The answer is B. It is decreases. With the negative feedback or in a closed loop control system, the system sensitivity to the parameter variations decreases. In a closed loop control system with positive value of feedback gain, the overall gain of the system increases. The options are decreases, increases, be unaffected, or any of the above. The answer is increases. With negative feedback, the overall gain is decreases. With positive feedback, the overall gain is increases. See, the characteristics of positive and negative feedbacks are given. The stability for negative feedback, it is high, and for positive feedback, it is low. The magnitude of transfer function is less than 1 in the case of negative feedback, and it is greater than 1 in the case of positive feedback. The sensitivity to the parameter variations for negative feedback, it is low, and the sensitivity to the parameter variations is high in the positive feedback. The gain of the system is low in negative feedback and it is high in the positive feedback. The error signals are decreased in negative feedback, whereas positive feedback, it is getting increased. Main applications of negative feedback are motor control. The main applications of the positive feedback are oscillators. Next question. Which of the following is an example of an open loop control system? The options are household refrigerators, respiratory system of an animal, stabilization of air pressure entering into the mask. Last option is execution of program by computer. So in the first three cases, in household refrigerator, it is based on the contents inside the refrigerator. That refrigeration level will vary. And for respiratory system or for stabilization of air pressure and everything, according to the requirement of a system, the respiration and stabilization of air pressure will vary. But in the case of fourth one, computer is a machine. The execution of program by a computer is what are the commands we are given as input, it will perform accordingly. So this is a best example for an open loop control system. The answer is D. Next question, due to which of the following reasons excessive bandwidth in control system should be avoided? So, excessive bandwidth should be avoided. Why? The options are, it leads to slow speed of response. Option B, it leads to low relative stability. Option C, noise is proportional to bandwidth. Option D, none of the above. The answer is noise is proportional to bandwidth. Whenever the bandwidth increases, the noise also increases, so that the bandwidth should be limited. See this in the explanation. The formula for thermal white noise power is defined by capital N is equal to KTB. Here B is a bandwidth and N is a noise. These two are directly proportionate to each other. Next question. A signal other than reference input that tends to affect the value of controlled variable is known as. Options: disturbance, command, control element, reference input. So here the command is an input variable, control element is an element which provides an control signal, and the reference input is an input. So the answer is disturbance. So that disturbance will affect the value of controlled variable. Next question. In a system, low friction coefficient facilitates where there are four options. One is reduced velocity error. Second one is increased velocity error. Third option is increased speed of response. Fourth option is reduced time constant. The answer is reduced velocity lag error. In a system, low friction coefficient facilitate reduced velocity lag error. Next question. An addition of zeros in a transfer function causes which of the following? There are four options. One is leak compensation, lag compensation, lag leak compensation, none of the above. The answer is lag compensation. So the addition of zeros in transfer function causes lag compensation, and the addition of poles in the transfer function causes leak compensation. See the next question. In pneumatic control system, the control valve used as final control element. It converts. There are four options. One is pressure signal to electric signal, pressure signal to position change, electric signal into pressure signal, position change to pressure signal. The answer is pressure signal to position change. This in pneumatic control system, the control valve used as a finite element, and it converts pressure signal into position change. Next question. When the initial conditions of a system are specified to be 0, it implies that the system is, when the initial conditions of a system are specified to be 0 means this is at rest but stores energy. The answer is at rest but stores energy. Next question. A tachometer is added to servo mechanism because there are four options. It is easily adjustable. It can adjust damping. It reduces steady state error. It converts velocity of a shaft to proportional DC voltage. The answer is B. It can adjust damping. So a tachometer is added to a servo mechanism for adjusting the damping for that purpose. Next question. A synchro transmitter is used with control transformer. The main purpose is, options are feedback, amplification, error detection, remote sensing. The answer is error detection. A synchro transmitter is used as an error detector to get the desired speed, and it is accompanied with the synchro transformer, which is used as an amplifier. Next question. The output of a first order hold between two consecutive sampling instances, the four options are constant, quadratic function, ramp function, exponential function. The answer is inverse Laplace equation of a Laplace of equation of first order hold gives ramp function, and hence the output of an first order hold between two consecutive sampling is ramp function. So the answer is C, ramp function. Next question. Which of the following is not the feature of modern control system? There are four options. One is quick response, second one is accuracy, third one is correct power level, fourth one is no oscillation. So in that, answer is last one. In model control system, it will have oscillation. Next question. The output of the feedback control system must be a function of, we have four options. In case of feedback control system, the output is the function of input and this feedback signals. Option D is the right answer. Next question. The principle of homogeneity and superposition is applicable to. We have four types of systems. One is linear time invariant system. Another one is non-linear time invariant system. Another one is linear time variant system. Another one is non-linear time variant system. So superposition theorem, this is applicable only to the linear system, and homogeneity is applicable only for the linear time invariant system. So the option A is the right answer, LTI system. Next question. In continuous data system, we have four different set of answers. One is data may be continuous of time at all points of the system. Next one is data is necessarily a continuous function of time at all points in the system. Next is the third option is data is continuous at the inputs and output part of the system, but not necessarily during intermediate processing of the data. Only the reference signal is continuous function of time. The answer is B. Data is necessarily a continuous function of time at all points in the system. Next question is, in regenerative feedback, the transfer function will be, actually the regenerative feedback is a positive feedback, so that the denominator must be 1 minus G of S into H of S. So the answer D is a right answer. C of S by R of S is equal to G of S divided by 1 minus G of S into H of S. It's a right answer. Next question. Consider a simple mass spring friction system as given in the figure. K1 and K2 are the spring. F is a friction, M is a mass, F is a force, and X is a displacement. The transfer function of a system will be. So we have, for this given system, we have four elements. One mass, one friction, two springs. So the force balance equation can be written for these elements. So for the case of mass, the force balance equation is M into S square. For the case of friction, the force balance equation will be F into S. For the case of spring, it is K1 and plus K2. From these options, The correct answer is B. 1 divided by m into s squared plus f into s plus k1 plus k2. Next question. In the below figure, it represent what? Is it a lead network, lag, PI, PD? Of course, it is not PI and PD controller. So the options will be in A and B, it is lag or lead. So by solving this entire system, so B1 into dx1 by dt minus dx2 by dt plus k1 into x1 minus x0 equal to k2 into x0. By solving this and viewing this transfer function, of course, this figure is an lag network. See the next question. Backlash is a stable control system may cause. So in backlash, in a stable control system, it creates, we have 4 options: under damping, over damping, high level oscillations and low level oscillations. The answer is low level oscillations. The backlash, when it is introduced in a stable control system, it produces low level oscillations in the system. Next, in case of DC servo motor, the back EMF is equivalent to electric friction, which tend to. So we have 4 options. It is slowly decreases the stability of the system. Second is improve the stability of the system. Very rapidly decreases the stability of the system. It have no effect of stability. The answer is B. It improves the stability of the system. So the Lagrangian is defined as, it is a term Lagrangian. Lagrangian means, actually it is difference between kinetic energy and potential energy. The gantry robot consists of a manipulator mounted on an overhead system that allows movement in a dash plane. So we have 4 options. It is horizontal, inclined, vertical and not of the mention. So the answer is the gantry robot allows motion only in horizontal plane, and this is made in this geometry to fulfill the respective work. The option is A is right. It is horizontal plane. Next, the transient response analysis is done for dash system. Of course, we can do the transient response analysis only for the stable system. Once a system happens to be unstable, we need not to proceed with its transient response analysis. See the question. The characteristics equation of a second order differential equation is given. So this can be converted as an equation in the below mentioned form. For d squared squared y by dt squared, this can be written as d squared. And the second one, 2 epsilon omega n, and dy by dt can be written as d. So the option A and C, these two are right. And in the third one, omega n squared into y equal to omega n squared into x. The option C is right. Actually, the d squared, 2 epsilon omega n into d plus omega n squared is equal to omega n squared is the right answer. So next question, for the differential equations in the above question, the damping coefficient is, of course, it is epsilon omega n. It's a formula. Damping coefficient is epsilon into omega n. And time constant for the second order differential equation, the time constant equation is 1 by epsilon omega n. So in this question, a characteristics equation is given. It is s squared plus 4.8 into s plus 72 is equal to 0. The damping ratio and natural frequencies are respectively. So it's a 4 answers is given, 3 data is given, and 1 is none of the above. So we can solve this equation. The characteristics equation is given. What we have to do is we have to compare the given equation with the general form of second order differential equation. It is actually s squared plus 2 epsilon omega n into s plus omega n squared equal to 0. By comparing the given equation with the general form equation, the 2 epsilon omega n is 4.8 and omega n squared is 72. So, when omega n squared is 72, while taking square root, omega n value will be around 8.48. And 2.2 epsilon omega n is 4.8. So, from this we can calculate the epsilon value. It is around 0.283. So, the answer B is right. 0.283 and 8.48 radians per second is the right answer. Next question. The natural frequency of a unity feedback control system of a transfer function g of s is equal to 10 divided by s into s plus 1 is. So, natural frequency is omega n. By comparing with the general form, the numerator is omega n square. Here, instead of omega n square, the value is given as 10. So, square root of 10, 3.16 radians per second. This is the answer for natural frequency of an system. For the second order differential equations, if the damping ratio is 1, then the poles will be, the damping ratio is 1 means it is critically damping. The poles will be or equal, negative and real. See, according to the damping factor value, the system can be classified as 4 types. When the damping factor is 1, then the system is said to be a critically damped one. When the damping factor is greater than 1, the system is said to be over damped. When the system is damping factor is less than 1, the system is said to be under damped. And when the damping factor is 0, the system is said to be undamped system. So, for the case of underdamped system, the poles are underdamped means the damping factor is less than 1. In this case, the poles are complex conjugate with the negative real parts. The next question, the unity feedback system is shown in the diagram. It has forward path gain k divided by s into s plus 10 and it is having unity feedback. H of s value is 1. So we have 4 options. One is 0 steady state position error, 0 steady state velocity error, steady state position error 10 by k by 10 units, steady state velocity error k by 10 units. See the solution. So the forward path gain g of s value is given, it is k divided by s into s plus 10. Here the h of s is equal to 1. So first we will calculate the position error coefficient. Kp is equal to limit s tends to 0 g of s into h of s. While substituting g of s and h of s and substituting s as 0, the kp values, the denominator goes to 0. So automatically the value of kp is infinite. So once a kp is infinite, we will calculate the steady state error. ESS equal to 1 by 1 plus kp, that is equal to 1 by infinity, it is around 0. So the option A is right. It is having 0 steady state position error. The option A is a right answer. So we'll go to the second question. The steady state error of stable type 0 unity feedback system for a unit step function. So this is option B, 1 by 1 plus kp. Type 0 system, steady state error is a formula. It is 1 by 1 plus kp. Next, see the problem. A unity feedback control system has the open loop transfer function g of s is equal to 4 into 1 plus 2s divided by s squared into s plus 2. If the input to the system is unity ramp, the steady state error will be. So g of s value is given, it is 4 into 1 plus 2s divided by s squared into s plus 2, and the feedback is mentioned as 1. So g of s into h of s is calculated by multiplying these two, and the ramp input r of s is given, it is 1 by s square. So static velocity coefficients kv is limit s tends to 0, s into g of s into h of s. While substituting all the values, the kv value comes around infinity. So when you are calculating steady state error, it is 0. So the steady state error for unit ramp input, it is kv, it is 0. The option A is a right answer. Next question. The step error coefficient of a system g of s is equal to 1 by s plus 6 into s plus 1 with unity feedback is, the step error, it is kp equal to limit s tends to 0 g of s into h of s. While substituting s as 0, the answer is 1 by 6. Option A is the right answer. It is 1 by 6. Next question. Consider a unity feedback control system with open loop transfer function g of s is equal to k divided by s into s plus 1. The steady state error of the system due to unit step input is step error kp equal to limit s tends to 0 g of s into h of s. So while substituting s as 0, the step error is kp is infinity. So while calculating steady state error, 1 by 1 plus kp, it is 0. The option is A, it is 0. Next question. For a second order system with open loop transfer function, T of s is equal to 9 divided by s squared plus 4s plus 9. The settling time for 2% band in seconds. So see the solution. The closed loop transfer function T of s is equal to 9 divided by s squared plus 4s plus 9, and comparing with second order equation, and here 2 epsilon omega n is 4, so that epsilon omega n is 2. The time constant is 1 by epsilon omega n square. So 4 by 2, it is a 2. The answer is 2. The option B is a right answer. See the next question. The steady state error of a system is shown in figure. So here k is 4 and g of s value is given and the feedback value is given. So g of s value is given and h of s value is given. So if we find kp, limit s tends to 0, g of s and h of s. So when we are multiplying these two and substituting s as 0, it comes at 4 by 2 and it comes as 2 by 4. While multiplying these two, you'll get 1. When you are calculating steady state error for kp, it is 1 by 1 plus kp. So 1 by 1 plus 1, it is 1 plus 2. So the answer is 0.5. Next question. A critically damped continuous time second order system when sampled will have in Z domain, it is simple pole, double pole on real axis, double pole on imaginary axis, a pair of complex conjugate poles. So for critically damped continuous time second order system, roots of a denominator are s squared plus 2 epsilon omega ns plus omega n squared equal to 0. When epsilon is equal to 1, for critically damped system, the damping ratio value is 1. So while substituting epsilon as 1, the answer is s squared plus 2 epsilon omega ns plus omega n squared equal to 0. So this we can simplify as s plus omega n the whole square is equal to 0, so that the roots are S is equal to minus omega n and minus omega n. So of course the answer is double poles on real axis. Option B is the right answer. See the next question. The second order system has a transfer function given by g of s is equal to 25 divided by s squared plus 8s plus 25. If the system is initially at rest and is subjected to a unit step input at t equal to 0, and the second peak in the response will occur. See the solution. G of s is 25 divided by s squared plus 8s plus 25. Here the omega n squared is 25 and omega n of is square root of 25, it is 5. So 2 epsilon omega ns is here, it is 8. While substituting omega here, epsilon is 0.8. So once it is 0.8, omega d we can calculate it is omega n square root of 1 minus epsilon squared. While substituting all the values, omega d values 3. For second peak, the peak time is n pi by omega d. That is 3 pi by 3. It is pi seconds. So the answer is option A is the right answer, pi seconds. The poles of a continuous time oscillators are imaginary. So always for the continuous time oscillator, the poles are imaginary. Next question. The response of the LCR circuit to a step input is overdamped, critically damped, and oscillatory damped. If the transfer function we have 4 options. So we'll go to the solution for first one. Overdamped. In case of overdamped, epsilon value is greater than 1 and the poles are on the negative real axis. So while substituting this in the equation, the roots of the denominators are minus epsilon omega n plus or minus omega n into square root of epsilon squared minus 1. For the case of critically damped, while substituting epsilon as equal to 1, we will get the roots are minus omega n and minus omega n. For third case, when epsilon is equal to 0, the poles are plus or minus j omega n. So the option is for overdamp, the poles are for option A, it is 1 and B it is 5, C it is 2. That is for overdamped case, the poles are on the negative real axis. For critically damped case, the multiple poles are on the negative real axis. And for the oscillatory case, the poles are on the imaginary axis. This is the right answer. Next question. Match the following codes with list 1 and list 2. The list 1 is very low response at very high frequencies, overshoot, synchro controller transformer output. The list 2s are low pass system, velocity damping, natural frequency, phase sensitive modulation and damping ratio. The answer is low response at very high frequencies happens in low pass systems. For high frequencies, it produces very low response. And due to the damping ratio, it produces overshoot. And phase sensitive modulation is there for case of synchro control transformer output. So these are all the correct matches. For next question, for a second order system, the damping ratio is 0 greater than epsilon greater than 1. That is, the damping factor value is between 0 to 1. Then the roots of the polynomial equations are, it is underdamped system, so that the roots are complex conjugate. Next question, if Laplace transform of f of t is equal to 2 into s plus 1 divided by s squared plus 2s plus 5, then f of 0 plus and f of infinity are given by. So see the solution. F of s is equal to 2 into s plus 1 divided by s squared plus 2s plus 5. F of 0 plus limit s into f of s. So while multiplying s in the numerator, we'll get 2s squared plus 2s divided by s squared plus 2s plus 5. So what we are doing is, we are taking s squared in both numerator and denominator outside. We'll get 2 plus 2 by s divided by 1 plus 2 by s plus 5 by s square. Here we are going to substitute s as infinity. What we'll get is 2 plus 2 by infinity in the numerator. You'll get 2 plus 0. Similarly, in the case of denominator, what you are doing is you are going to substitute s as infinity. What you are getting is 1 plus 0 plus 0. So you'll get 1 in the denominator. 2 by 1 is 2. And so, of course, the option B is the right answer. We'll solve the next one also. F of infinity. So it is limit s tends to 0. For f of 0 plus, we are going to substitute s as infinity. For f of infinity, we are going to substitute s as 0. So similarly, we are going to solve this one. So s is, while substituting s as 0, the numerator will be 0 and the denominator will be 5. 0 by 5, it is 0. The answer is 2, 0 respectively. The option B is the right answer. Next question. The final value theorem is used to find steady state value of the system output. The final value theorem is for finding the steady state value of the system output is the right answer. Next question. If f of s is equal to omega by s squared plus omega squared, then the value of limit t tends to infinity f of t is cannot be determined, is unity, and it is 0 and it is infinity. The answer is it cannot be determined. Next question. Consider a feedback control system with loop transfer function g of s into h of s value is given. The type of the system is, actually the type of a system is number of poles at the origin. So poles means we have to consider the denominator polynomial. In the denominator polynomial, we have 3 poles. One is s is equal to 0, another one is s is equal to minus 1 by 2, another one is s is equal to minus 1. So the number of poles at the origin is 1. So the type of the system is 1. Option B is the right answer. Next question. The unit impulse response of a linear time invariant system is unit step function u of t. For t greater than 0, the response of the system to an excitation e of minus at u of t and a greater than 0 will be. So here the h of s value is given, it is 1 by s, right? So and system excitation, it is r of t, it is given as e power minus at into u of t. So from this, while taking Laplace transform, r of s is equal to 1 by s plus a. So the response of the system h of s into r of s is 1 by s into 1 s plus a. So by partial fraction, we can separate these terms. It will come as 1 by a into 1 by s minus 1 by s plus a. So while taking inverse Laplace, 1 by a is a constant. So the inverse Laplace of 1 by s is 1 and 1 by s plus a is e power minus at. The option B is the right answer. Next question. If the characteristics equation of a closed loop system is s squared plus 2s plus 2 is equal to 0, then the system is. So when the characteristics equation is given, to find the system, to find the damping factor and the classification of the system, you have to find the epsilon value. So from that characteristics equation, we can compare with the second order differential equation, it is s squared plus 2 epsilon omega n squared plus omega n squared equal to 0. By comparing these two equations, 2 epsilon omega n is equal to 2 and epsilon will be 1 by omega n. Here omega n squared is 2. Omega n is square root of 2. It is epsilon is 1 by root 2, then which is less than 1. Of course, it is under damped system. Next question. Consider a system with the transfer function s plus 6 divided by k s squared plus s plus 6. Its damping ratio will be 0.5 when value of k is. So see the solution, g of s value is given. So here the damping factor ratio is 0.5. By comparing these two equations, omega n squared is equal to 6 by k. Then the omega n is square root of 6 by k and 2 epsilon omega n is 1 by k. So while substituting all these things, the k, we can solve the value of k, it is 1 by 6. The answer is 1 by 6. Option C is the right answer. Next question. A causal system having the transfer function h of s is equal to 1 by s plus 2 is excited with 10 u of t. The time at which the output reaches 99% of a steady state value. The four options are given. So we'll solve the problem. Here the h of s is 1 by s plus 2 and the r of t value is given, it is 10 u of t. When you take a Laplace transform, r of s is equal to 10 by s. So c of s is equal to r of s into h of s. While multiplying these two, 10 by s into s plus 2. So by partial fraction, we can divide this 2 into two terms. So that c of s is equal to 5 into 5 divided by s minus 5 divided by s plus 2. While taking inverse Laplace, 5 into 1 minus e power minus 2t, so that the steady state value is 5. 99% of a steady state value reaches at. So you will have to substitute in this equation, that is 5 into 1 minus e power 2 minus 2t equal to 5 into 99%, so that 0.99. While solving this, t value is 2.3 seconds. So option C is a right answer. Next question. The transfer function of a plant is 5 divided by s into s plus 5 into s squared plus s plus 1. The second order approximation of t of s using dominant pole concept is option D is a right answer. So poles near the imaginary axis dominates nature of time response and are called dominant poles. The factor that has to be eliminated should be a time constant form. Here the t of s is equal to 1 by s squared plus s plus 1. Option D is the right answer. Next, group 1 list 4 transfer functions and group 2 gives list of step responses y of t. Match the step responses with the corresponding transfer functions. So this group 1, we have 4 transfer functions p, q, r and s. This is a group 2. It contains 4 transfer step responses. So the answer is, we have 4 options is given. So we have to solve this. For see that given transfer functions are. So while comparing these two, that is comparing the given transfer function with the general form of transfer function, for the first case p equal to 25 divided by s squared plus 25. For the first case, the epsilon value is equal to 0. So that means that the p is an undamped system. So that this third diagram is matching for undamped system. So P is 3. and take the second transfer function. Q is equal to 36 divided by s squared plus 20s plus 36. According to this, epsilon value, while solving this epsilon value, it is 1.67. So it means that it is over damped. It is greater than 1. So that this fourth diagram is step response for a over damped system. Next transfer function, r equal to 36 divided by s squared plus 12s plus 36. So here the omega n is 6. So epsilon, while solving this, epsilon value comes around 1. It means that the third system transfer function is an critically damped system. And fourth case, it is 0.5. It is under damped system. So that the answer is D answer. First one is for underdamped system, and for critically damped system, and for undamped system and underdamped system, right? We'll go to the next question. The unit step response of a underdamped second order system has steady state value of -2. Which of the following transfer function has these properties? Steady state value of -2. So second order transfer function is omega n square divided by s square plus 2 epsilon omega ns plus omega n square. For underdamped system, it is epsilon values less than 1. So the option C and D are wrong because the system is unstable as epsilon is negative. See the option C and D, these two are having negative sign. So this is a wrong answer. So the correct answer lies between A and B only. So in the option A, 2 epsilon omega n is 2.59 and epsilon is 1.22. So here it is epsilon is greater than 1. For the case of option B, the epsilon is 0.69. While solving this, omega n squared is 1.61. So omega n is square root of 1.91, it is 1.38, and 2 epsilon omega ns is 1.91. While substituting omega n value in this equation, 1.91 divided by 2 into 1.38, it comes around 0.69. So the epsilon is less than 1. So the system is underdamped. The option B is a right answer. Next question, the differential equation is given. It is 100 d squared y by dt squared minus 20 dy by dt plus y is equal to x of t. Describes a system with an input x of t and an output y of t. The system which is initially relaxed and is excited by unit step input. The output y of t can be represented by the waveform. We have 4 waveforms are given. The solution is 100 d squared y by dt squared minus 20 dy by dt plus y is equal to x of t. While taking Laplace transform on both sides, we'll get for d squared y by dt squared, we'll get s squared into y of s. For dy by dt, it is s into y of s plus y of s is equal to x of s. It is 1 by s. And taking y of s outside, we'll get 100 s square minus 20 s plus 1 is equal to 1 by s. So y of s is equal to 1 by s into 10s minus 1 the whole square. So of course the poles are at 0, 1 by 10, 1 by 10. So all the poles are on the right hand side of the plane, so that the system is unstable. So while viewing all the 4 pictures, the option A is an for unstable system. So output y of t is an unstable. Option A is a right answer. Next, the open loop transfer function of a DC motor is given as omega by V of A, VA of S is equal to 10 divided by 1 plus 10s when connected in feedback. is shown below. The approximate value of Ka that will reduce time constant of closed loop system by 100 times as compared to the open loop system is, see the open loop transfer function 10 divided by 1 plus 10s, and Ka is a controller. So open loop transfer function will be 10 Ka divided by 1 plus 10s. So we'll take 10 outside, both in the numerator and denominator. We'll get Ka divided by S plus 1 by 10. So while taking inverse Laplace, g of t equal to e power minus t by 10, and loop time constant is 10. So while solving this, h of t values Ka e power minus 1 by Ka plus 0.1 into t. So the time constant is 1 by Ka plus 1 by 10. So by solving this, Ka is around 10. The option C is right answer. So next question, for a second order closed loop system shown in the diagram, the natural frequency of oscillation is, it is 4 divided by S into S plus 2. So the natural frequency of oscillation omega n we have to calculate. So G of S divided by 1 plus G of S into H of S. So by solving this one and comparing with the second order general equation, omega n squared value is 4 and omega n natural frequency of oscillation is 2. Next, the damped frequency of underdamped second order system is omega d equal to omega n into square root of 1 minus epsilon square. In most of the system, an increase in gain leads to smaller damping ratio. The second derivative input signal modify the time constant and suppress the oscillation. The second derivative input signal always modify the time constant, and also it decreases the oscillations of the system. The positional error coefficient of a unity feedback, it is Kp. Kp is limit S tends to 0, G of S into H of S. Here the feedback is 1, so that limit S tends to 0, G of S is the right answer, answer B is the right answer. The velocity error coefficient is limit S tends to 0, S into G of S into H of S. Here the feedback is unity, so limit S tends to 0, G of S, S into G of S. Answer C is the right answer. For acceleration coefficient, the Ka value is limit S tends to 0, S squared into G of S into H of S. Here it is not given, so the answer is D, none of this. For any given closed loop system, only one static coefficient has finite non-zero value. It is right. For type 0 system, positional error coefficient will be non-zero. For type 1 system, velocity error coefficient will be non-zero. And for type 2 system, acceleration coefficient, error coefficient will be non-zero. So, if any case, any one static error coefficient has finite non-zero value for any closed loop system. So, the answer A is the right answer. For type 0 system, it has no pole at origin. For the case of type 1 system, it has one pole at the origin. For the case of type 2 system, it has two poles at the origin. So based on the number of poles at the origin, types of the system is classified. For type 0 system, it has finite non-zero value of Kp, and type 0 system steady state error is 1 by 1 plus Kp. For type 1 system, it has one pole at origin. And type 1 system has finite non-zero value of Kv, and its steady state error for unit ramp function will be 1 by Kv. And for type 2 system, it has two poles at the origin, And type 2 system has finite non-zero values of Ka, and the steady state error for unit parabolic input is equal to 1 by Ka. So an introduction of integral action changes the system into type 1 to type 2. The answer B is right. Introduction of integral action, it changes the system from type 1 to type 2. Conditionally stable system is one which exhibits poor stability for reduced values of open loop gain. So conditionally stable system is one which exhibits poor stability for reduced values of open loop gain. The steady state error coefficient for a system are Kp equal to 0, Kv equal to finite constant, and Ka is equal to infinity. The system is, if Kv has a finite constant, it is, of course, it is a type 1 system. If Kp have a finite constant, the system will be type 0 system. If Ka has a finite constant, the system is type 2 system. The positional velocity errors of type 2 systems are 0, 0. The steady state acceleration error of a type 1 system is infinity. The steady state error for a unit ramp input to the characteristics equation is 0.25. The open loop transfer function g of s is given, it is k divided by s squared into 1 plus s. Here the s squared is given in the denominator polynomial. Of course, it means that there are two poles at the origin, so it is type 2 system. The positional and velocity acceleration error coefficient of an open loop transfer function is, so this is a type 2 system. So acceleration, there is no need to solve this equation. Actually, it is a type 2 system. So acceleration error coefficient will be having a finite non-zero value. So in the fourth options, option A is acceleration error coefficient is given as infinity. In option B, it is given as 0, and option C, it is given as 0. In option D, it is given as K divided by 1000. By viewing this, there is no need to solve this. By viewing the four options, we can opt it as option D is the right answer, because option D only contains acceleration error coefficient non-zero. The option is D is the right answer. The unity feedback control system have transfer function g of s is equal to k divided by s into s plus 1. The steady state error for a unit step position and unit acceleration inputs are respectively. These are given. So this is a type 1 system. So automatically the positional error value is 0 and the unit acceleration input steady state error is infinity. So the option B is a right answer. Thank you. With this, we will wind up the session. We will see in the next video.